Today, our primary focus is to discuss on an investigation of a complex behavior of chlorine and alkali within blast furnace system and to systematically optimize the blast furnace slag to improve the capacity to retain these harmful element. The goal is to translate this understanding into more stable operations. Moving to our core objective on slide 2, first we aim it to clarify the intervened behavior of chlorine and alkali and their effects across all phases, that is gas, liquid and solid within the furnace. Second, we need to quantify how chlorine and alkali compounds contribute to sinter degradation. So this is one of the most important aspects that is going to be discussed. Uh, and third, crucially for the operational control, we conducted a discussion and extract on a systematic study both in lab and on site to identify the key parameters that govern the slag's alkali retention and desulphurization capabilities. And finally, we have a also discussion on the properties of final slag, but those things is not included in the content of the slide. Now coming to the our next slide, which is on the details of the problematic behavior of chlorine, and which is the our core area of discussion. The key point here is the chlorine is not effectively removed through the slag. This is the biggest challenge. Due to the low condensation temperature of chloride, it primarily circulate and accumulate in the blast furnace shaft, leaving mainly via dust and top gas. So, under our blast furnace condition, chlorine has a very strong affinity for alkali metals, predominantly potassium and sodium, which forming a very stable chlorides like potassium chloride and sodium chloride. This is where the major operational issue arises. These alkali chlorides condense and re-vaporize, creating a circulating load. And these actually, it is not about a condensation and vaporization, rather it is also transferring important heat reserve from one place to other place. Now this deposition within the burden, especially on the sinter, causes a mechanical disintegration, and which becomes a huge root cause of a number of abnormalities getting rise in the furnace. This leads to increased fines in the shaft, and which in turn result in poor gas permeability, and which also result in a pressure loss imbalance. And once this pressure loss imbalance occur, there is a many irregularities gets rises in the blast furnace operation. Now, coming to our next slide, which discuss on the uh, direct impact on our burden material, starting with the sinter reduction degradation index. Alkali generally accelerate the reduction kinetics and lower the onset temperature of the reduction to between 400 degrees centigrade and 700 degrees centigrade. Now, this causes the premature transformation of hematite to magnetite. And once this premature transformation of hematite to magnetite occur, which creating a lot of internal stresses and cracks that weak the sinter structure drastically. And by these phenomena, a fines generation starts increasing. However, it is important to note that a specific chlorides like MgCl2 and potassium chloride. These two things we have to understand, these two components, magnesium chloride and potassium chloride. These can actually act as a inhibitor to reduction and disintegration around 500 degrees centigrade, showing the chemistry is complex. So one way we comes to know that this premature transformation point from magnetite to that is hematite to magnetite is generating a lot of fines due to its premature transformation. And the second is but the second thing is that many chlorides which are especially many chlorides, not magnesium chlorides and potassium chloride, especially act as a barrier to this radiation and disintegration, particularly in the band of 500 degree centigrade. Uh, uh, and this makes the entire system more complex. Now coming to shifting from sinter to coke. So moving to coke quality, CSR CRI if is concerned, potassium load on coke is significant effect. High potassium rate directly increase the coke reactivity index. In earlier also many presentation we discussed on this topic. This is because the potassium catalyze the Woodward reaction and accelerating the reaction of coke with CO2. So this reduction degradation, this rather degradation in particular is not just chemical. Alkali attack alter the coke microstructure also, and the resulting change in coke strength after reaction is further increased by this physical aberration and gas condition inside the furnace, as all knows about this. So alkali pressure is a key contributor to coke degradation, but not the only one. Now coming to our next slide, which is about the conclusion and the path forward. So to summarize the problem, we can say that chlorine input is generally detrimental, no doubt about it. It leads to a circulating alkali chloride that cause shaft accumulation, burden degradation and operational irregularities. Alkali promote low temperature sinter disintegration, while their chlorides forms can also inhibit reduction in a specific temperature window that we have seen in the earlier slide, like potassium, magnesium chlorides. They are also act as a barricade, and that is to also up to 500 degrees centigrade. On the positive side, our slag optimization work is to look into. We have clarified that we can actively manage the slag ability to remove alkali and sulfur by controlling its chemistry. The optimal window for the high alkali retention and good desulphurization is achieved with a lower basicity slag coupled with a increased alumina and MgO content up to certain extent only, and this leads to our future strategy for the burden planning to achieve this optimal slag chemistry. As we know, we have two primary burdening routes. The first using high basicity sinter balanced with the acidic palette or lumpur. So this is option number one. And as far the option number two is concerned, using a moderate basicity sinter combined with the flux palette and a silica addition. So this also comes under our second option. So we can say that the recommendations are pretty clear. Reducing the input of both chlorine and alkalis from the raw material will provide the most significant improvement to blast furnace stability and performance. Our slag optimization gives us the tool to manage what does enter the system. So, by understanding the chloride alkali cycle and the proactively optimizing our slag chemistry through careful burden design, we can directly target the pressure losses, reducing the fines generation and improving the overall for furnace stability.